Welcome to the fourth and final tutorial on models of the atom. This is the hydrogen emission spectrum investigation, where we'll answer the question what happens when we expose hydrogen to a large amount of energy, and what can this tell us about the structure of the atom. So first, before we begin with the hydrogen emission spectrum, we need to talk a little bit about diffraction of white light. So this is a picture of a diffracting grating. A diffracting grating is a material with very, very, very small slits in it. And when we pass light through it, the light bends, and the angle of that bend depends on the frequency of light. So when we expose a diffracting grating to white light, for example, a light bulb, which is incandescent light, it's pure white light, when we put that near the diffracting grating, it produces a rainbow, a perfect rainbow with continuous color changes. It's absolutely beautiful. So this diffracting grating bends the light such that the blue light is bent at an angle that is larger than the red light, and so all of the colors split out in a rainbow. So now what we want to do is look at what happens when we have hydrogen, the hydrogen spectrum running through this diffracting grating. So here we'll have a tube that is evacuated, and then hydrogen is put in that tube with some electrodes, and we can put it into a high voltage container and turn it on, and we get some light. And when we pass this light through the diffracting grating, we don't get a rainbow. In fact, most of it is black, except these bands of very distinct colors. So we have a kind of a beautiful violet and a deep blue and a teal and a red color that are coming out, but none of the other colors are there. So in about 1885, Johann Balmer came up with this idea that he could model these lines, the wavelengths of these lines, with this equation. It doesn't really matter, the equation, but he found that if this n was a whole number, 3, 4, 5, and 6, 3 would describe the wavelength of this line, n equals 4 would describe this, n equals 5 would describe this, and n equals 2 would describe the wavelength of that line. So it was interesting that he could find a mathematical model that didn't explain, but described the wavelengths that were produced when hydrogen was passed through this diffracting grating. But it took 30 years for somebody to explain why this might work. And the person to explain this was named Niels Bohr. And here's how he explained this phenomenon. He essentially said, okay, the atom is made up of this very, very, very small positive nucleus. And it also has these energy levels in it, where the first energy level that's closest to the nucleus has the lower potential energy, and then there's another energy level, and then another, and then another, and another, and another. And he called these energy levels n equals 1, 2, 3, 4, 5, and 6. And he said that in its ground state, in other words, when there's no extra energy added to the hydrogen, the electron is in this lower energy level. And when energy is added in to the atom, the electron absorbs this energy and goes up in energy to another energy level. Now, this electron could go up to the 6th energy level, or the 5th, 4th, 3rd, 2nd, depending on how much energy was absorbed. So when this is a high energy state here, and it doesn't last very long, so when the electron comes back down, and it turns out it comes back down to the 2nd energy level, energy comes out, and because of the law of conservation of energy, the energy that comes out has a certain amount of energy, and that energy is, in this case, this violet light that you see. Well, if the electron actually just went up to the 5th energy level, we would actually see, when it comes back down, the blue light. If the electron was excited to the fourth energy level, we would see that teal light. And if the energy was, or if the electron went to the third energy level, we would see the red light. So essentially, Bohr said that the first energy shell is n equals 1, and that's the lowest potential energy. If we think about that, the electron is attracted to the nucleus. This is in the lowest state. As we pull the electron further away, we have a higher potential energy. And you can see that when the electrons fall back in energy, that light's emitted, and the light has one particular wavelength. So we find that the energy of the electron is very quantized. In other words, there's one particular energy. So what you might notice is that we didn't see, quote unquote, any transitions back down to n equals 1. And that's because if we went from n equals 6 to n equals 1, the energy is such that the wavelength is in the ultraviolet range where we can't see it. So later we were able to detect these other transitions down to 1. So we were able to see many, many more transitions. This is an amazing feat. In the Bohr model, we learn that electrons have discrete energies, and we don't see a continuous rainbow because the electrons don't fall down into just any place around the nucleus. They fall down to specific energy shells. This model works extremely well in predicting the Balmer equation that you saw previously for hydrogen. It works extremely well for any one electron system. However, it does not predict what the wavelengths of any other spectra that we observe for any other elements. So that's why we need to have a different model. And that model is the quantum mechanical model, which predicts the electron clouds, the probability of finding electrons in certain regions around the nucleus.